This is Karen Hauk, your friendly Solar Week coordinator, coming to you live from beautiful University of California at Berkeley. And I'm so pleased to present to you Dr. Nicky Fox, the project scientist for Parker Solar Probe. I just wanted to remind everyone, I see in the chat that people are very excited and they're tuning in, and we're really glad to have you. If you want, your microphones are muted, so if you, depending on what kind of device you're on, if you wave your cursor around or look around the screen, you should see a chat box, and we'll be kind of collecting some questions to ask to Nicky as she goes along. And beyond that, ready to go. Take it away, Nicky.
All right. Hi, guys. So I'm Nicky Fox. I am the project scientist for Parker Solar Probe, or as I like to call it, the coolest, hottest mission under the sun. And I'm coming to you live today from my living room because it's a snow day here and my kids are off school. So I'm working from home. Let's see, I wanted to take a few minutes to tell you about this amazing mission because we are getting ready to launch later this year. If you have questions at any point, you do not need to wait for me to finish. I've already told Karen, you can interrupt. It's completely fine. But I'm gonna, start rolling through and see how much of this we can get through. So Brian, if we go to the next slide, please. I wanted to start off just by talking about the eclipse across America. I'm sure a lot of you were lucky enough to see it. I know several people weren't able to see it because they had travel problems, but if I was in Beatrice in Nebraska, enjoying a very beautiful eclipse, very emotional. It was the first time I'd ever seen an eclipse, and it was extremely cloudy right up until the moment of totality for us. So it was a particularly dramatic time. But the important thing about eclipses, of course, is it's the first time that it allows us to see the sun's corona, that hazy atmosphere that we were all blown away by during the eclipse. And, the corona has many mysteries in it. But before we get into those, next slide, please. Let me take you back to 1859, which was the first time that we realized that the sun and the earth were actually kind of connected. And so James Carrington, who you see in the middle there, was busily sketching sunspots, looking through his brass telescope. He was an amateur astronomer. And while he was looking through, he saw incredible flash of light. And he, ran off to ask somebody, hey, wow, did you see this? When they got back, it had disappeared. So he thought maybe he'd imagined it. But just a few hours later, compass needles at Earth began to spin around. The aurora was seen down as far as Cuba. And the telegraph system, that was what we used for communication in 1859, went down and remained down for about 4 days. Now, you may not think that sounds particularly bad, but imagine having no internet, no power, nothing for 4 days or more. And that's what that would translate to if that happened to us today. So we know that the sun is very active and it throws a lot of activity our way, and it can adversely affect our planet. Next slide, please. So, where are we in the solar cycle? I'm sure you all know that the sun has a cycle. We basically count sunspots. The more sunspots we see, the higher the activity is likely to be. When we see the maximum number of sunspots in any given time, we call that solar maximum, as you can see in the peaks on these little graphs. And when we see the minimum, and often it is 0, we call that solar minimum. A solar cycle is usually about 11 years. The last one was a little longer. It was a very unusual solar cycle for us. But as you can see, we are down in the descending phase of the solar cycle, getting ready and looking forward to a solar maximum around 2021, 2022. So with the next slide, space weather, just a quick look. I mentioned that we see a lot of activity at Earth when we see these big events. We see aurora, that's really beautiful. However, we see a lot of other disturbances. We can see effects to airline routes. They won't be able to fly over the poles. They have to actually go around, or sometimes they can't fly at all. We see impacts to spacecraft, either from particles associated with solar flares that can actually damage the solar cells. We can see just our ionosphere, the area around, very close to the surface of the planet, where the radio waves kind of bounce through. We can see that change. We can see it get very dense. It can start absorbing signals instead of bouncing them off, or it can just change the way they move. We can have electrical currents that flow that will actually damage power grids and run through power pipelines like the Alaska pipeline. So there's lots and lots and lots of different activity that we can see that's all driven by our sun. So next slide. So let me tell you a little bit about the mysteries of the sun. So we're looking at the sun's corona here at different wavelengths. These different wavelengths correspond to different temperatures of the material that we're looking at. So we're going to start again, and we'll see that the surface is at about 6,000 degrees. As we start to move away, we start to see the temperature increase. And so you're looking at now, you can see that the material is now brightest away from the surface of the sun. And so that means that the corona itself is about 300 times hotter than the surface of the sun. And this doesn't make sense. It kind of breaks the laws of nature. It breaks the laws of physics. If you're by a campfire and you're nice and warm and you stand up and walk away, you don't get hotter, you get colder. But in the corona, that's what happens as you move away from the surface of the sun. The corona is getting up to about 3 million degrees. So on the next slide, we'll summarize our mystery. Mystery number 1 is that the temperature rises as you move away from the surface of the sun. Who knows why? Our next mystery on the next slide is that where we see this incredible temperature maximum, the material itself gets so energized. It's not just heat, but it's also energized so much that it can escape away from the pull of that star. And if you think the sun is a giant star and it is, it holds all of that material, but then suddenly the material gets so energized that it says, bye-bye sun, and moves away from the sun, stretches out and bathes all of the planets. That's why the Earth is seeing space weather. Something happens on the sun, it gets energized, it moves away from the sun, and it can impact the Earth. And so this is what you're looking at basically is what we call the solar wind. It's this atmosphere, the coronal atmosphere. It gets heated, it gets energized, it moves away in all directions, and it continues to move. And so our second mystery on the next slide, we summarize it. Why? How does this solar wind get continually accelerated? Why is there a solar wind? Why does it manage to break away from this big pull of the sun? And these are 2 mysteries that have been around for decades and decades. So what are we going to do about it? Let's go to the next slide. So this particular mission, there's a lot of history. We've already talked about 1859. Now I'm going to take you to 1958. In 1958, you may already know, but that was the first time we ever really launched anything into space. Explorer 1, which was launched, James Van Allen was the lead investigator for that, and that led to us discovering that the Earth had radiation belts. So shortly after that, the launch was July 31st, 1958. And so shortly after that, there were agencies that were starting to form. So NASA was starting to form, the National Science Foundation, and the Department of Defense were all interested in, what are we going to do with this newfangled thing called space? What are those big missions that we need to have a big agency, a big infrastructure to do? And so they asked for a committee to be formed, and it was chaired by John Simpson from the University of Chicago and James Van Allen. And they got a group of very eminent scientists together, and they came up with 14 missions that were just, big and shiny and fantastic, and we really needed to do them. And of those 14, 13 of them in some way have already happened. And the last one is a probe to fly into the sun's corona, or a solar probe. We have named the mission Parker Solar Probe. And if you look on the right-hand side, you'll see some lovely pictures of Gene Parker. Why Gene Parker? Because he wrote the paper in 1958 where he actually predicted there would be this solar wind. He didn't immediately call it the solar wind, but he called it like outflowing corpuscular radiation. And later it was confirmed in 1962 by Mariner 2 data, because they were flying out in this atmosphere and they saw these particles just as Gene had predicted. And so we've renamed the mission for Gene Parker. It's also historic because it's the first time NASA has ever named a mission after somebody in their own lifetime. And so again, steeped in history for us. So we go to the next slide. So this was a big honor for me. I just put this up because it's kind of fun, but I actually got to introduce Gene Parker to his spacecraft. And so I was able to say, Parker, meet Parker. And he came to the Applied Physics Lab and he actually got to see the spacecraft and meet a lot of the engineers that were working on it. And he was very gracious. He said to me, all I did was write a paper. And I said, yeah, it's pretty good paper, Gene. As papers go, it's pretty good. And he said, yeah, but if you get there and we discover that I'm wrong, I'll just write another paper. He said, but you guys that are actually building this mission, the engineers, you haven't got any margin of error. If you get it wrong, the mission is over. And so, he was very, very gracious and just very humble and complimentary to all of the people that are really making his mission come true. So if we go to the next slide. And so how are we going to study the sun and the solar wind? Well, we're going to actually send a spacecraft to journey into the sun's corona. And so, we're calling it Parker Solar Probe. There's a beautiful shot of it nice and close to the sun. And it will be taking all these critical data in the corona to allow us to answer those mysteries that we already talked about. Why is the corona hotter than the surface? Why is the solar wind continually accelerated? The next slide, please. So I just like to throw this one in. Why haven't we done this before? Why has it taken us 60 years to be able to do this mission? And so it really is because we've needed technology to catch up with our dreams. And in 1958, I know none of you guys have probably ever seen this, but this used to be a telephone. So this is a rotary dial telephone, and that was the only way that you could communicate with people outside your house. Now, we all have fantastic iPhones or Android phones. You think of the amount of technology you hold in the palm of your hand. You probably use that phone for everything except for making a phone call. And if you think of the amount of stuff that you can do with that phone, in 1958, that probably would have been 6 or 7 city blocks worth of engineering. And so that's the kind of reasons that we've had to wait this long. Next slide.
Nikki, we have a couple of interesting questions in the chat.
For it.
Okay, the first one we have here, question from a student. Could the rise in temperature above the sun's surface into the corona be possibly caused by magnetic effects, gravity trying to pull down or stop the release of energy into space, causing a friction buildup, thus causing a rise in temperature?
Wow, would this student like a job immediately?
They should work for NASA.
Nice job, nice question. So we don't know. There are many theories. Definitely something in the storing and the release in the magnetic field we know has got some big role in this. And in fact, one of the big things that we're going to do is measure the magnetic fields very close to the sun to see, how big they are, how dynamic they are, how much they are changing. One big theory, in fact, it's Gene Parker's theory, which he released in, I think, 1975, is he thinks it's little mini flares. So how you see flares associated with the big events? He actually thinks there are little flares that are happening pretty much all the time and that are sort of releasing energy just enough that it gets released into this region above the surface. But we absolutely know that the magnetic fields are one of the big keys to how this is happening. Close to the sun, the magnetic field, just like the Earth, the sun has a magnetic field. Close to the sun, it rotates with the sun. So it moves nicely along, and all of the coronal material is stuck to those field lines and it rotates with it. Where we see this big energy the plasma itself gets so energized, it moves away and it pulls the magnetic field with us. And so the magnetic field, the orientation and the dynamics we know are a major key to what's going on. We just don't quite know what it is yet. Do you have another question?
Yes, we do have some more questions. Sorry, I was muted. Let's see. Okay, a question from a student. How far will the spacecraft go into the corona, and how will it deal with the heat?
All right, can I hold that question? Because I have a great graphic that is going to tell you all about that one coming up.
Okay.
Okay.
And then we have another question about how NASA will take, how will NASA take the names of the people who have sent their names, including this person,
yes,
for the Parker Solar mission to the sun?
Yeah, so we are going to, there's going to be a chip that is going to be inside the spacecraft. We are burning all the names of everybody who sends them in at the website. We are burning all those names into the chip, and they will be transported with the spacecraft into the corona. And if you haven't done it yet, please sign up. If you have, people that are no longer with us, grandparents that you'd like to honor and maybe go on the journey with them, you can put their names in too. I put in my grandparents yesterday. And so, it's like a journey we're all taking together. So go.nasa.gov/hot ticket, and you can put your name into the sun.
Great. I love the idea of putting loved ones' names in. Here's another question. If a coronal mass ejection reached the probe, would it destroy it?
No, it won't. We're designed for that. Actually, my biggest fear, people always think my biggest fear is going to be a big event and, oh my God, it's going to, wipe us out. My biggest fear is that we won't see an event and the sun will be really, really quiet and we won't get to do all the stuff that we really want to do. We are anxious to see the full type of activity that the sun can throw at us. I'm not saying I wouldn't be worried about the probe. To me, she's like another child. So, I'm going to send her into this very dangerous environment. So, of course, I'm going to worry that she's going to survive. But we have designed to really withstand these big events.
And okay, we have, I see that Igor added the hot ticket link in the chat too. That's
great.
Do you want to take a couple more questions, or do you want to go forward and wait a little bit?
Let's go forward and do the so I can answer the questions about how close and how we're going to survive, and then we'll finish off with as many questions as you guys have time for.
Okay, great.
Okay. So we're going to launch this year, July 31st, our launch window opens. It's a 20-day launch window. You may wonder why we have a small launch window when, after all, the sun is indeed there all the time, every day. But we actually are going to use Venus. And I have a nice little graphic in a minute that's going to show you. We will fly past Venus 7 times in the mission. And so our launch window is governed by where Venus is. It needs to be exactly in the right place for us to be able to go into the sun. We'll launch from Kennedy. And we are on a Delta IV Heavy with an upper stage. So we're on the biggest launch vehicle possible, and we have an upper stage. So we're moving pretty fast. So next slide, please. So here we are. I hope you can see this. This is the fairing opening, and out comes Solar Probe to see the sun, see space for the first time. There you see us lifting off the second stage. And if you watch, you'll see that third stage fire just there. And then now Solar Probe will lift off the final stage. We're moving at about 430,000 miles an hour. The first thing we do is we pop out our solar panels so we can get some energy and some power. Down the back there, you see deploying our magnetometer boom. It's where our magnetic field instruments are, which we've already talked about being so important. And there you see the electric field antenna coming out. Everything is stowed while we launch to keep it as protected as possible. And then we put it out as soon as we get in space. There we are flying past Venus for the first time. We use Venus not like other missions have done to speed up. Like, you may remember New Horizons flew past Jupiter and it sped up and got to Pluto quicker. We're kind of doing like a little handbrake turn around Venus. And so we're actually using it to just change the trajectory a little bit so that we move straight in towards the sun. We do not want to be orbiting around the sun with the Earth. We want to have no influence from the Earth at all. And so we use Venus to get rid of that, any residual pull that the Earth may have on us. You notice probably we're a very ecliptic orbit. We go very close to the sun on one side, and we come out around Venus on the other side. We encounter Venus 7 times in our just under 7-year mission. And so each time we encounter Venus, we walk a little bit closer into the sun. So let's go to the next slide. Oh, that's coolest. Yes, it's well, I'm so competitive. We're fastest, we're closest, we're hottest, I tell you. So how hot will we be? We are going to be in the region of 3 million degree plasma. You may think, oh my goodness, does that mean you have to survive 3 million degrees? Well, there's a difference in temperature and heat. And so if you think, and please don't try this at home, but if you just think about this, if you put your oven on and you know it's up at about 400 degrees, you can put your hand inside the oven and you won't get burned unless you touch a surface. The moment you touch a surface, you allow the energy, the heat energy, to come into your fingers. In the solar wind, in the corona, even though it's dense compared to the rest of space, it really isn't very dense at all. There aren't an awful lot of particles. So the amount of heat that actually comes into the front side of our heat shield is about 2,500 degrees Fahrenheit, which is still very hot, but 2,500 or 1,400 degrees centigrade. The amount of heat on the main body of the spacecraft itself, it's at about room temperature. It's a little above room temperature, maybe about 85 degrees Fahrenheit. So our heat shield is really, really good. And that is how we will survive these temperatures. We are moving fast. We have to keep the heat shield between us and the sun at all times. One of the things you may have noticed in the video is we pull our solar panels in as we get closer and closer to the sun. The amount of power that we generate on a full solar wing close to the Earth is the same as we can generate in just one tiny row of solar cells when we're close to the sun, because we can see about nearly 500 times as much sun as we see here on Earth. It's about 478 suns that the solar probe will see. Fastest, I already said, 430,000 miles an hour, 118 miles a second. So New York to Tokyo in under a minute. We are blistering around the sun. Let's go to the next slide. And so how close? I love this one. Okay, so if I put the sun and the Earth on either side of a football field, we would then place Mercury at the sun's 35-yard line. We would put Venus at the Earth's 28-yard line. We know that the longest coronal loops can extend out to about the 15-yard line. Our current record holder, Helios, has gone closest to the sun. It got as far as the sun's 29-yard line. Off it goes. And now welcoming to the arena, to the main event, Parker Solar Probe, the newest mission to study the sun, which is going to go right the way into the sun's 4-yard line. So when I say to people, you know, hey, we're going to go to 3.9 million miles above the sun's surface, they look at me and they go, that's not that close. 4 million miles. Wow. I thought you were really doing something amazing, Nikki. But when I point this out, that it would be, you know, on a meter stick, we're at 4 centimeters. On a football field, we're at 4 yards. That is pretty close to the sun's surface. So next slide. Real quick, just to give you some idea, we're a very small spacecraft. We weigh just 685 kilograms. The spacecraft height itself is 3 meters. The TPS is our heat shield. So you see that sort of hexagonal structure at the top. It's about 2.3 meters or 8 feet. We lovingly call it our 8-foot frisbee. The main bus or the main body of the spacecraft is just about 1 meter across. And so we're very small. We say we're always on a diet. We need to be thrown off that rocket so fast to be able to travel as fast as we can. We don't want to get pulled into the sun. We want to kind of surf around the corona. So just like you surf on a wave and you don't fall into the water, we want to surf around the corona and not get pulled in. So we have to be moving really, really fast. And so we're always as light as possible. If we go to the next slide, I can show you a little bit more about the protection system, so our TPS as we call it. At closest approach, I already told you guys, it's about 2,500 degrees Fahrenheit. Payload itself is at near room temperature. It sits on a titanium structure. You can see that over the bottom right-hand picture there. And that is specially designed to hold our heat shield in place. Where we attach the heat shield, it's got kind of like a shoulder, like the ball joint in your shoulder. It allows movement in all directions because as the heat shield gets hotter and colder, we do 24 orbits. So it's not just the heat, it has to also survive getting cold too. And so that heat shield is actually going to kind of change shape. And so it needs to be able to move on those contact points so it doesn't just pop off the moment it gets hot. Next slide. And then I'll show you the solar arrays. So what you're looking at on the left-hand side there is that is the final articulated piece of the solar panel. So if you look at the diagram in the middle, you can see some sort of, at the bottom there, you can see kind of a silvery looking strip. That is that final panel in the window. And that top row of cells, the teeny tiny ones, that's what's generating all of our power when we get close to the sun. You may know, well, solar cells are fantastic and they produce a lot of energy for us. And we've got nearly 500 suns, so we should be fine. Solar cells also do not like to get hot, and they don't work if they get hot. So we tuck them in, put them in the shadow as much as possible. And then the ones that actually have to survive the environment, we cool them by running water. It's like you have veins in your hand and the blood runs through and it can, cool you down. We actually cool down the panels using water, which we run through them all the time. So next slide. I think we're nearly done. Okay, so this is just a quick look at the instruments. Most of the instruments sit on the main body of the spacecraft, tucked behind and in the shadow, with the exception of those antenna that you see sticking out. They're the electric field antennas. And also the SPC, the Solar Probe Cup. It is a fairly big instrument that sits in the full environment. It takes no protection from the heat shield, and it measures everything that is coming towards us from the sun as we move in. If we flip the spacecraft over on the next slide, you can see all the instruments that are on the main body of the spacecraft. There we go. Whisper at the top there, that is a white light imager. It is taking pictures of the solar wind, basically what is about to hit the spacecraft. You see a suite there called ESIS, Epi Low and Epi High. They are measuring the high energy particles associated with flares and shocks and coronal mass ejections. And then at the bottom, you can see sweep. There's one called Span A+. On the other side of the spacecraft, there was one called Span B. When you put the fields of view of those instruments together, they fit together like the seams of a baseball, and they allow us to have a full 360-degree view of everything around the spacecraft. And last but certainly not least, as pointed out by our wonderful first question, there's our magnetometers on the back there. We have 3 of them because we're not quite sure what we're going to see when we get there, and we want to be able to make sure we can measure it completely. We don't want it to be so high that our instruments can't make that measurement, nor so low. So we carry 3 magnetometers to cover a full range of whatever we would expect to see. So next slide. Oh, and this is going to show you. I can take questions while you guys are watching this if you like, Karen. This is just basically showing you us building the spacecraft. It starts with putting together the primary structure. It's a hexagonal bus. You can see how small it is. We lower in there our harness. So that is basically all the wiring and everything that you need to make the spacecraft work. There we are lowering the top deck. So you can see those black vein structures are the radiators that we use to cool the water from the solar panels. That's our high gain antenna. That's how we send the signals back to Earth. This is the most terrifying thing ever. We hang the spacecraft and we swing it. That allows us to fully characterize the magnetic fields on the spacecraft. We want to do that before we go into space. Putting on the solar arrays so we can make sure we have lots of power on the spacecraft. And then this is them doing the finishing touches to our thermal protection system. They're doing the final bonding. and then they will, in the minute, you'll see them lowering that whole structure onto the spacecraft. One side of the spacecraft you see is white. That is the front side, and that reflects most of the sunlight. The rest of it is black. It is a carbon structure, and it allows us to absorb all the heat from the solar wind and from the corona. And there is Solar Probe looking like Solar Probe. Okay, and I think the next one should be just the information about how you can, oh, where are we now? I'm sorry, I forgot about that. We are actually about to come out. We've finished our thermal vacuum testing. So we've gone into a big chamber, we've taken all the air out, we've made it just like space. We've taken it hot, we've taken it cold, we've simulated faults, we've done all kinds of things with the spacecraft. We've actually just broken vacuum, and tomorrow we will lift the spacecraft back out of the chamber. She'll go back into the clean room, and then in about a week she will ship down to Florida, down to the Cape, where we'll do our final testing. She'll get fuel put into her, and then she goes into the fairing, and the next stop is a Delta IV Heavy. All right, let's go to the next one. Okay, that's how you can follow the excitement. I know we're running out of time, so Karen, hit me with some questions.
Okay, got a lot of questions here. Let's see. Well, this is a good question. Is the solar wind specific to our sun? Would it be different if we were looking at a bluer or redder star?
That's a hard one to answer. We know that there are, stellar winds from most stars. Of stars that we know that are like our sun, we certainly see the same type of feature. We see, stellar flares. We see lots of activity. It's hard to really characterize them without fully understanding ours. So that's one of the reasons that we actually want to go. Our sun is in our own backyard. And even though it's hard for us to go and, it's taken us 60 years to figure out how to go in and study our own star, we will immediately be able to use all that data and liken it to other ones. But yes, we certainly see stellar winds in many other stars. Different stages of a star, they are going to have slightly different properties, but they all seem to have some escaping atmosphere.
Okay, so we have some questions about the probe. Why is it going so fast, and how will it slow down?
Okay, it's going so fast. One, because we need to escape the pull of the Earth. The Earth has a lot of momentum, and so it will have its own angular momentum as it is orbiting the sun. And we do not want to follow the Earth. We want to go straight into the sun. So we have to be going with enough power and enough energy that we don't get kind of drawn into the Earth's orbit. We also are moving so fast because we do not want to fall into the sun. And so we have to, again, like a surfer surfing on a wave, we want to be moving so that we can stay in the corona and not get pulled into that gigantic star. So that's why we have to go so fast.
Great. Well, I see we're sort of past our time, but maybe one more, if it's okay with you.
It's fine with me. I'm good for a while.
Okay. Let's see here. What is it? Okay. Oh, there's been several questions about how the probe protects itself from the extreme heat it's going to encounter.
Yeah, and so we do that with many different ways. Our heat shield is the easiest example. We create this shadow. Unlike Earth, in space there is no atmosphere, so there's no convection. And so I often get asked, well, it's fine, you're protecting this bit, but what about all the stuff coming in the side? But there isn't stuff coming in the side. If you sit on a beach on a hot day, you get hot because the sand underneath you has absorbed a lot of heat, and the convection is moving all of that atmosphere around you, so you remain hot. Just even if you sat under my heat shield, you would still be hot here on Earth. But in space, there is no convection. And so it's just what's coming to us from the sun. And if we can protect everything from that, then everything else stays cool. Other ways we protected are materials that can withstand not just the incredible temperature, but also this change in temperature. 24 orbits, I mentioned, going hot and cold and hot and cold. The materials cannot change their property. It can't become brittle and fall apart. So a big effort into making sure we have the right materials that will withstand these different temperatures. The front side of the heat shield, that material was developed specially for Solar Probe. It is an alumina coating. It is plasma sprayed. So basically you heat it up into incredible energy, you make it a plasma, and then you shoot it at the surface, and it spreads and forms that coating. So many ways, cooling the solar panels with water, and tucking them in, keeping everything in the shade, making sure that we've got lots and lots of little sun sensors all over the spacecraft. None of them are ever supposed to see the sun. The moment one does, the spacecraft is fully autonomous. It knows how to correct itself. So if it sees something here, then a thruster over here will fire, and it will keep reorienting itself. So many, many ways that we protect ourselves.
Great. Thank you so much, Nikki. I think that we don't have time for more questions, but Solar Week is still going on. So this is the time that you can go to the solarweek.org and go to ask a question, and you can type your questions to all the solar scientists on the bulletin board. And thank you so much, Nikki. This has been a great presentation. And
no problem.
I'll be watching Parker Solar Probe and with a lot of excitement.
Yeah, and I promise I'll hop on to solarweek.org later today and answer as many questions as you have for me. So
great. Thank you, everyone, for coming. And happy Solar Week.
Happy Solar Week.